Greetings everyone. Today we're going to be talking about Bernoulli's equation and many of its applications in our everyday life. Just to point out a few things, here we have an albatross, which is flying. And one of the ways that it flies and takes advantage is the flow of air over its wing in order to not flap so much and expend too much energy. Another thing that we have here is a jet, which of course has airfoils, and that helps provide lift to the jet. But also what's going on in the background here with the water. So the water seems to be shooting up into the air, and we're going to talk about some of the reason for that. And the last picture that we have here is a carburetor. So basically fuel is pumped into the carburetor, and what we need to do is we need to basically atomize. You want lots of little droplets of fuel in order to get very good combustion. And what happens is you blow air across this. The air blows past here at a high velocity, and that pulls the gas out of this, out of the carburetor, and then atomizes it. So we're going to talk about Bernoulli's equation and how it applies to each of these. So first, to talk just real briefly about fluid flow again, bring these up. There's laminar flow. This means you have a nice smooth flow profile where your streamlines are like so. And also this continuity equation is very important. Basically this means that the mass of your fluid is conserved. So this brings us to Bernoulli's equation. A few things that we need to go back over is that the pressure in the fluid depends on the applied pressure. So if you have some system like this, you have some pressure over on this end, some pressure over on this end, and the water is going to flow something like this, I don't know, and flowing to the right. So if you have some pressure difference here, it's going to cause the fluid to flow. The pressure in the fluid also depends on the depth of the fluid, so it's also going to depend on how deep we go. And it's also going to depend on how fast this fluid is going. So in this equation, we kind of ignored this effect, that if you speed up a fluid, it actually decreases the pressure. And we're going to talk about that. So some of the assumptions of Bernoulli's equation are that we have nice laminar flow, that there's no rotation. So this is important because we don't want to think about angular momentum of our fluid. We also have very low viscosity. So this means that in our container, basically, our flow profile doesn't depend on how far away from the walls that you get. So basically there's no walls either, and no energy losses. And that this fluid is incompressible. And what this means is that this rho isn't changing. All right. So Bernoulli showed that basically this is the equation. So you have some pressure, you have this depth term, rho gh, and we have this term. So if you look carefully here, you'll notice that this equation is actually energy conservation. So this term right here kind of looks like a kinetic energy, but it's like a kinetic energy over times of volume, basically. So, and then this right here kind of looks like a potential energy due to gravity, and again, like times of volume. And then this term right here, this is pressure. So what are the units of pressure? Pressure is kilogram meters per second squared, all over meters squared. So if you multiply this by a volume again, so that'd be times a meter cubed, so times the volume, then this would again have the units of a joule. So each of these terms are like units per volume. So This equation here is really just energy conservation, and we're going to put this into use. So our first problem deals with a fire hose. So we want to put out a fire way up on the top of this building that is 12 meters tall. And somehow we need to, this is a completely 1D problem, so we're basically just squirting the water straight up. We're going to hook this up, and we need to know what's going to happen here. Basically, what's the velocity that we need, what is the pressure that we need in order to make the water go up and put out this fire. On one end, we're going to have P1 plus 1/2 rho V1 squared plus rho G H1. So this is our one, and here's our final. And then we're going to have P2 plus 1/2 rho V2 squared plus rho G H2. So there's actually two ways that we could go about solving this. One, we could go, well, what is the velocity that we need to have at this point of the fluid in order to get us up here? And if you start to think like that, then you can use energy conservation. And then now you've got a 1/2 mv squared is equal to mgh. And then this gives you, your v squared is going to be equal to 2gh. And then you could put this back into here and call this your 2, basically, is what we're saying. And then you could go and solve the problem for what is this pressure difference that you need. But Bernoulli's equation actually already has this energy conservation in it. So what we need to think about is what's up here, and this is another V2 equals 0. So if this is the case, then this guy is 0, this guy is 0, and all we need to think about is P1 minus P2 is going to be equal to rho G delta H. So we just subtracted the two H's. So this directly gives us the pressure difference that we need right here between here and the atmospheric pressure. So this is going to give us our gauge pressure right here. So then all we need to talk about is what is this rho GH, and so this is 1,000 kilogram meter per meters cubed, and then now 9.81 meters per second squared, and then times our 12 meters. And then this is going to give us 117,200 pascals. And just for reference, one atmosphere is this big. So we basically need to put another atmospheric pressure pushing on this water. So what is this in PSI? So we take this 11,000, then we do our unit conversion, so 101,325 Pascal, and then times 14.7 PSI. So this gives us about 17 PSI. So for this next problem, we're going to find the force that... So for this next problem, we're going to find the lift force on the wing of this jet. So we're going to start with Bernoulli's equation again. So P1 plus 1/2 rho V1 squared plus rho G H1 is going to be equal to P2 plus 1/2 rho V2 squared plus rho G H2. And now, if we're talking about lift force is, we need to, so here we're going to get a pressure, and so we want to relate pressure with force. So this is actually going to be PA. So pressure is force over area, so then force is equal to pressure times area. So we want to find this pressure difference across the wing. So if we look at this wing, then the velocity on the top is going to be this 2 50. And the velocity of the air on the bottom is going to be 200 meters per second. This difference in velocity is going to cause a pressure difference, and this pressure difference is what we're looking for. So we really want this, P1 minus P2. And then we can get rid of a few things, which are these two terms. So here are the difference in height between the top and the bottom is pretty small, so we're going to ignore that. So then this is going to be 1/2 rho V2 squared minus V1 squared. So this is going to be equal to 1/2, and then the rho here is not rho of water. It's going to be the rho of air, which is like 1.16. It depends on altitude. Here you're higher up, so this density is smaller, kilograms per cubic meter. And then now the difference in the squared velocities. So 250 squared minus 200 squared. And this is going to give you 1.3 times 10 to the 4th Pascal. So then what is the force on the wing? It's going to be this pressure, 1.3 times 10 to the 4th Pascal, then times this 82 meters squared. And this is going to give us about 10 to the 6 newtons. And this is a huge force. That's nothing to throw out. But we also should consider the mass of our 747 here. And the mass is going to be like 333,000 kilograms, which is like 3 times 10 to the 6 newtons. And so the lift force that Bernoulli is that we get out of Bernoulli's equation gives us a lot, and there's two wings, so that gets us pretty close. But it's certainly not everything that's going on here. Another important fact is that how the wings are tilted in order to provide a little bit of additional lift. This brings us to our last example, which is a Pitot tube, which was invented by Henri Pitot, who used a similar device to this to measure the flow speed in the River Seine. But today it's used in all different kinds of aircraft in order to measure their airspeed, which was especially important in the days before GPS. So how this device works is that the aircraft is moving like this, but if we move into the reference frame of the aircraft, then it looks like the air is coming at us like this, in a nice laminar flow. What's going to happen to the streamlines is that they're going to bend around this device like this. And so then the airspeed here at B is going to be V of the aircraft. We did some minimal adjustment to the flow here, but basically this airspeed here should be the same as the airspeed here. But what's interesting is that at this point A, is that here the velocity of the air is 0, because this is the one point along the streamlines where the air goes this way or it goes this way, and right in the middle it's actually stopped, and the air is actually called a stall here. At point B, we have in this tube right here, there's a bunch of holes poked into this thing, and these are holes all into here. And so at this point, at point A and point B, we can invoke Bernoulli's equation. And so we have P1 equals plus 1/2 rho V1 squared plus rho G. H1 is going to be equal to P2 plus 1/2 rho V2 squared plus rho G H2. So right away, between A and B, there's no difference in height. But what this says is, and also V at A is 0. So this means that P at A is equal to P at B plus rho, and here we need to be careful which rho we're dealing with, because here we're dealing with air. When we start to talk about what's happening in this tube, we have to deal with rho of the alcohol. So then, 1/2 rho of the air, V squared. So this is actually what we're looking for. So let's make sure that we know that. So moving on, so this gives us the pressure here at B that is not detectable. So the pressure at B we just found, since we know the pressure at A, and we also know that this pressure at A is going to be just atmospheric pressure, so we know that. So this pressure difference between A and B causes the fluid to move up like this. And here we have, let's change color again. So here we have a height difference. So this is our H, I don't know, call it H liquid. So this height difference we know from, P equals P0, like P1 plus rho GH. This is the same thing as Bernoulli's equation, just without any fluid flow. So if V is 0, you get this guy again. And this is exactly what's happening in this liquid. So here we have PA minus PB is going to be rho GH. And we also have, from here, is equal to 1/2 rho air V squared. Here we have the liquid, and we need to keep the liquid and the air kind of separate. So then our V is going to be the square root, so we're going to multiply by 2 rho of the liquid, G H of this liquid, all over rho of the air. And if we plug in our numbers, so we know H, we know rho of the liquid, and we know rho of air. So rho of air is much smaller. It's about 1. So here it's 1.03 kilograms per meter cubed. So when we plug this in, we're going to get about 75 meters per second, which is a usual flight speed for a Cessna.